Welcome again to another podcast, podcast number 14 here, which is all about acid-base indicators. Well, this should be a relatively short podcast where we're going to kind of introduce indicators again and just a little bit of terminology and what they kind of do in a titration, as the rest of this chapter is going to be about titration reactions. So an indicator is used to determine what we call the equivalence point in a titration. All right, the equivalence point is what we care about. All right, that's what we actually want. All right, now, what tells us when that happens is usually something that we call the end point, and that's when our indicator changes color. Now, we have to pick the right indicator so that it changes color at the equivalence point. They don't just do that magically. We are picking the correct indicator. So don't confuse equivalence point with the word endpoint. They are different definitions. Know the difference between those two definitions. They are not interchangeable. Well, indicators are weak organic acids by nature, and so they just happen to be weak organic acids that have one very special property, that they can change colors. And they change colors when we say that they are in an acid or when they're in a base. Now, the problem with some of our definitions of these things is you think, okay, that means that they're going to change color. Like whenever there's a pH of 8, that's basic. It's going to be one color. When it's a pH of 6, that's acidic. That's another color. All right, that's the case for something like bromethymol blue, right? But if you have something like phenolphthalein, it changes color around a pH of like 9. All right, so what that means is that a high pH, right, it's going to be one color. At a lower than that pH, it's going to be another color. So while we call it the color in acid or the color in base, what we really mean is that it's going to be a color at a low pH versus a color at a higher pH. The change doesn't have to come at 7 necessarily. All right, I hate this example for what an organic indicator looks like, but remember that it's a weak acid, so I've got that H out in front, and then this is IN for indicator. All right, now, yes, there is the element on the periodic table, IN for indium. It is not that. This is just standing in for indicator. And so just like any weak acid dissociation, we could solve for a Ka for this. The Ka is equal to our H plus times our indicator divided by the weak acid concentration. Here we have a lot of information on this slide about, when we're going to get a color change and whether we're going to have the indicator be the acid color or whether we're going to have our indicator be the basic color. And we can calculate that by looking at the ratio of the indicator itself, the weak acid itself, divided by the concentration of what it is dissociated into, and whether it's greater than 10, less than 0.1, or around 1, what the color is going to be. All right, we're never going to use any of that stuff up here, but the very bottom stuff down here at the bottom is important. And it states that, right, the color is going to change when the pH is roughly equal to the pKa. All right, so the color change is going to happen at a pH that is roughly equal to the pKa of the indicator. So that can be helpful to us when we're picking indicators later on. If you want your indicator to say change colors at a pH of 4, well, you need to find something whose pKa is right around 4 as well. You're not going to pick one that has a pKa around, say, 9.5. That'd be a terrible choice, right? So that's going to help us pick our indicators later on. The example that I have here of an indicator is probably a bad example because it does change pH at 7, or it does change color at 7. but they don't all change at 7. The only reason that this one changes at 7 is because the Ka for this is 1 times 10 to the minus 7th. And so the pKa is the negative log of that value, 1 times 10 to the minus 7, which is equal to 7. All right, and so this would be the pH at color change. Just so happens to be that for bromethymol blue. What I do want us to see, though, is that notice that it's yellow when it is at low pHs. It is blue at high pHs, and we can see like a little bit of transition there between, because yellow and blue make green, and we see that transition. But I just want us to notice that, right, it is a consistent yellow. It is not like we are going from yellow and we're slowly changing towards green. The color change is very quick. And then once we get up here to the blue, right, it's just the same blue throughout all of those colors. We're not seeing any differences, so you can't make any determinations on the pH by like, this is a darker blue at 11 than it was at 9. That's not the case, right? We can't use that. The only thing that this does is it tells us one specific point where the color change occurs. And we have to pick that close to where, right, the reaction is going to be at our equilibria there. And we have an equal number of moles of acid and base. That's what we're going to be looking for. And that's what we're going to be talking about over the next couple of podcasts when we start talking about our actual titrations of different types of acids and base reactions. I'll see you then.